So just to recap, my goal here was to build some dynamic RAM on a breadboard, learn how dynamic RAM works, and hopefully eventually be able to hook that up to a 6502 computer. So what I'm going to do today is start out by building the column amplifier on the breadboard, then add a memory cell. Hopefully these will work well together. Then I will expand the array as much as I can in both directions, so as many columns and rows as I can fit on the breadboard. So let's go ahead and see if we can build the end of column circuitry, which, as I said before, would be called a sense amplifier in a proper DRAM module. I'm not exactly building a sense amplifier here, but it's a sort of equivalent circuit that will capture the state of the active rows bits on each column and kind of pump it into an amplification loop, which will then feed back into the DRAM cells and recharge their capacitors. So this is the circuit that I'm going to use for this. It's very similar to what I showed before, but I've drawn this using MOSFETs instead of inverters to make it clearer what I'm actually going to build, because I'm not going to use canned inverters here. It's pretty easy to make your own inverters out of MOSFETs, so I thought I might as well keep this just to the discrete components. So this line on the left is a bit line, which I've called Bn, for n being the number of the bit. So as we expand this out, I'm going to put more bits on. For now, this is going to be the only one though. It's going through one n-channel MOSFET here to invert the bit line signal and amplify it up. I've got a fairly low resistance here, so that will that will be able to pull this right up to 5 volts swiftly, and then it goes through a second n-channel MOSFET here to invert it back. So this right hand side here will exactly match the state of the left hand side, but again it'll be amplified back up to near enough 5 volts through this 1k resistor. So it's going to have a 1k impedance on the positive side, and pretty much 0 on the negative side, because we should be getting a high enough voltage through here that this MOSFET achieves a very low resistance when it's on. Then the right hand side of this can be tapped straight off as a data line. So when we're reading from the cell, we'll get again a 1k impedance on the reads, which I think is going to be okay. It's not super low, but it's fine, I think. And there's a feedback loop here through a resistor back to the bit line, and I've used quite a high resistor here, 100k. This is something that might need tweaking. Essentially, the higher this value is, the easier it is for the bit line to influence the state of this little amplifier, but the longer it takes for the amplifier to recharge the bit line. And particularly during writes as well, that means that a write will take longer, because the value coming in on the data line, it'll take longer to charge the capacitor through a larger resistor. Initially I'm going to be running this myself, just manually clocking it, so I will be able to run it quite slowly, and that shouldn't be a problem. But later on, when I connect this up to a microprocessor, I might need to tweak the value of this resistor and or change the whole circuit. We'll have to see whether it even works at all at those kinds of speeds. So I should probably explain how I'm going to lay this out on the breadboard, because it might be a little bit different to how you've seen these done before or how you do it yourself. For these kinds of circuits, I like to avoid having lots of separate things connected by jumper wires as much as I can. I like to keep it quite compact, and that'll come in handy, because I do intend to make this quite a dense circuit in the end with a lot of memory cells. So I'm going to put the components in a way which probably won't show up too well on the camera. So I thought it would be worth just talking through quickly how I'm going to do that first. I might do it slightly differently as we go, but this is how I'm planning to do it anyway. And what it boils down to is identifying how many nets there are in the circuit and allocating each net a column on the breadboard. This is a bit like what you do with a PCB layout. A net is a wire connection between components. So this circuit has 5 nets, I believe. One of the nets is the bit line itself, which joins onto the gate of the first MOSFET and this end of this resistor. So that's all one net, that's all connected together. Another net is ground, which joins onto this source of this MOSFET and the source of this MOSFET. And even though that's not joined together on the circuit, obviously they're both connected to ground, so that's another net. Another net is the power, which again are not connected together, but they are connected to the same power rail. Another net is this one in the middle here, which goes from the drain of this left-hand MOSFET up to this resistor and onto the gate of the second MOSFET. And the last net is the drain of this MOSFET, which joins to that resistor up there, it joins to this resistor down here, and it is also the data line output. So that's 5 nets. I'm actually going to only use 4 columns on the breadboard because the power net I'm going to just bridge straight across to with the resistors. For the ground I am going to allocate a column, and that's because I don't really want to stretch the legs of the MOSFETs all the way to the power rail. You can do that, but I prefer not to. I find it's a bit messy doing that, so I will use a jumper to join those down, and I'll give it an entire column on the breadboard to itself. So in terms of which order I'm going to put these in, I think I will put the ground first. I usually put the connections on the MOSFETs or transistors in the order that they are actually in the pinout for the MOSFET, and in these MOSFETs it goes source, gate, drain. And I want the sources to both be connected to ground, so I'll put that on the left hand side in the first column of the breadboard. The next connection along, I will use I'll put the gate of this MOSFET in the next one along, which is the bit line net, and then I'll put the gate of this one in the second column, and I'll put the gate of the second MOSFET, which is also the drain of the first one, in the third column. So this MOSFET is just going to span the first 3 columns of the breadboard. I'll use a resistor then to connect that to the power rail. Then for the second MOSFET, the gate we've already talked about, the source we've already talked about, and I'll bend the leg so that it skips a row before that, and then the drain goes in the 4th column, and that is the data output. And then this resistor will just bridge that one to power, and this resistor will kind of bridge from the 4th column to the second one, I think that was. So that's what I'm going to build. I thought I'd explain it because it might not be very obvious on camera. I'm going to build this on the bottom half of the breadboard. So let's start from here, for want of a better place. So that's the ground net. And then I had the first MOSFET, which joins from the ground net to the bit line in the second column on its gate, and its drain is just loose in that 3rd column for now. Then I'm going to put the second MOSFET in next, and that one shares the same source connection on the ground. Its gate goes in where the drain of the first MOSFET is, and its drain goes into the next column along. What do we have next? We had a connection back from that 4th column to the second one through a 100k resistor, which I can put in here. It gets a bit fiddly. Again, I'm building this small because I do anticipate building quite a lot of them on one breadboard later. And then I have 2 1k resistors, and I can put them in. They're to ground, aren't they? No, they're to the positive rail, those 1k resistors. Let's make that a bit shorter. So that's for the 3rd column in the breadboard, and this is for the 4th column in the breadboard. Is that fitted in? Yeah. So that's actually the entire cell complete there. It is missing the inputs and outputs. Obviously we'll need to join them on. So what I'm going to do is I'm going to make a temporary connection from the bit line, which was the 2nd column on the breadboard here. I'll connect that over here, and I'll rig something up with a couple of buttons, I think. See if I can fit that on there. I hate these buttons. They really don't work well on breadboards. They seem to be exactly the wrong way around, but I find if I put them slightly diagonal like that, they actually fit in better. I also forget which way they're connected and which way the button controls the connection. But to fix that one, I just always use opposite corners of them, so I don't even need to care about that. So we're going to have one button for on and one button for off. Yeah, let's make the left button be on. So I'm going to connect the far side of the left button to the positive rail, and the right button needs to be off. So I'm going to connect the far side of the right button to the negative rail. So those buttons should be turning that on and off now. I could connect a multimeter up to verify that. Maybe we should just put an indicator LED in instead. Now the problem with the LED is it will draw current from the circuit, and it might actually interfere with the functioning of the device. Is that going to work well? Well, let's just put one in and see what happens. That data line output is a reasonably high impedance. It already has a 1K pull-up resistor on it, so I don't actually need an extra current limiting resistor on this LED, I don't think. I'm going to move that connection down to the bottom, and then the LED can just sit along the top for now. This is only kind of temporary, just to see what happens. So yeah, that's that, and let's turn on the power and see what happens. So the LED is currently on. So when I push the on button, nothing happens. When I push the off button, it turns off and it stays off. So this is what I kind of mentioned last time, was a fairly standard static RAM memory cell, just two cross-coupled inverters, and you can turn them on and off just by kind of forcing their state, and it then remembers that state afterwards. So that works pretty well. Next up, let's build an actual memory cell, because then we'll have something to connect this bit line to. So here's the memory cell I showed before in the last video. This is kind of where I ended up in terms of what I was planning to build. We have the bit line coming up here. We have a row selection line along the top, which is active high. The row selection line drives these two MOSFETs. These are arranged in opposite directions, and that functions as a bidirectional switch, meaning that when the row line is low, current can't flow in either direction along the two MOSFETs. But when the row line is high, current can flow in whichever way the voltages are lined up, and that will allow us to charge or discharge the capacitor through that gate, and control how that happens. Then we have the capacitor, which is actually the charge storage which forms the long-term memory of the memory cell. So when that's charged, it is a on bit, and when it's discharged, it's an off bit. I've drawn that here connected to ground. I think I'm actually going to join that to the positive rail instead. The reason for that is that in some experiments I did earlier, I found that the discharge was really asymmetric when it was connected to ground, and I tried a few other things like connecting it to 2.5 volts and things like that, and I found that having that one connected to the positive rail actually gave me the most symmetrical discharge. And over on the right hand side here, this is more for debugging than anything else, but it's quite cool to have a visualization of the state of every memory cell, I think, so I do want to put that in. We have a MOSFET which is acting as a low side switch for a current limited LED. I am also going to change this around slightly, and again that's based on some experiments I did earlier on, just with threshold voltages of the MOSFETs and things like that. And I think it's going to work better with the LED on the low side, and I'll leave the resistor on the high side. And the reason for that is the gate switch voltage will be sort of propped up a bit by the LED's voltage, so the kind of point where the LED turns on will be sort of around 2.8 to 3 volts or so, which I think is going to be a better kind of level for indicating whether this is charged or not. So I'm going to move the LED down to the bottom side of this MOSFET. That resistor there, I think 1K is probably good value for that. It'll limit the overall current flow to 5 milliamps with a 5 volt supply. And yeah, so again, I'm going to build this on the breadboard. I'm going to build it quite compact. First of all, let's think about these two MOSFETs here, because the MOSFETs are the most constrained pinouts we have here. So again, the pinout order of these particular MOSFETs is source, gate, drain. The sources are on the outside of this connection. So I'm probably going to put this MOSFET, I'm going to put the source, then gate, then drain for this MOSFET. This one over here has its drain connected to the same line as the drain of the first one. It also has its gate connected to the same net as the gate of the first one. So it will share both of those two connections, and it's just its drain that's in a, so it's just its source that's in a different column. So I'll put that in an adjacent column. Then this MOSFET over here needs its gate to be connected to the source of this one. And then we obviously have its drain and source to connect as well. Its source goes to ground. Again, I'm not going to bridge it to ground. I'm going to give it its own row on the breadboard for ground. And I think I'm going to have to leave an extra blank row, an extra blank column when I'm putting these MOSFETs in, so that there's space for that on one side or the other. Oh, sorry, I forgot. This is actually going to have an LED on it, isn't it? I could take the LED to ground. So that's going to take about 5 or 6 rows on the breadboard, 5 or 6 columns on the breadboard, I think. And I'll put them in that kind of order. So now I've added a memory cell to the circuit in addition to the column amplifier that I built before. I moved the LED on the column amplifier to the side and powered it through a MOSFET because in its existing location it was drawing too much current from a sensitive part of the circuit. The green wire is the row select line, which I've got hooked up to a button here, which is normally low and goes high when I push the button. And the yellow wire is a data line. So this is kind of a tri-state line. At the moment it's floating, and these buttons allow me to put it high or low. So for example, when I put it high, you can see that it forced the column amplifier into the high state, and when I push it low, it brings the column amplifier into the low state, as indicated by the LED. So the way this works is when the row select line goes high, the state of the memory cell is copied into the column amplifier, and the column amplifier kind of feeds that back and remembers its state just like it's doing here. And at the same time it feeds the amplified signal back up into the memory cell through the row select MOSFETs and recharges or discharges the capacitor. So that's what ensures that over time, if the capacitor loses its charge, we can refresh its state. And that's generally how a read cycle works. If we want to actually write to the memory cell, all we need to do is force the data line high or low while the row select line is active. So once again, normally the data line is not driven high or low at all. It's kind of a tri-state signal. So normally it's not being driven at all, and in that condition the memory port performs a read operation, and it's possible to sense the high or low state of the memory cell through the data line, which is exactly what this LED is doing. It's just sort of tacked into the middle of that data line. But that data output is kind of a high impedance. It's not super high, but it's also not very low. So if you have a lower impedance source driving that data line high or low, then it will win, and the memory will perform a write operation. So for example, as I showed before, pulsing the data lines allows me to turn the column amplifier on and off. And if I turn the column amplifier on and then pulse the row select line, the column amplifier just gets turned off again, because the row select line caused the state of the memory cell to get copied back down into the column amplifier. If I hold it in the high state while I'm pressing the row select line, however, the memory cell goes on. And it'll stay in that condition for quite a while. It's not, because I'm not pressing the row select line at the moment, the memory cell is disconnected pretty much from the rest of the circuit, and as you can see, it's losing its charge a bit there. But I can always push the row select line again to refresh it, and it goes back into the on state. It takes quite a long time for it to discharge when the column amplifier is in the high state, but when the column amplifier is in the low state, it actually discharges much quicker. Not immediately, but just a bit quicker. So that kind of asymmetry bothered me a bit. I'm not totally sure what causes it. I think there's just some differences in the leakage current through some of the MOSFET gates in the two different states we have there. It's not really a problem. Dynamic memory always needs to be refreshed on a regular basis. It just means that when the column amplifier is in the low state and the memory cell is in the high state, the memory cell is going to lose its contents more quickly. So that's the time that's going to determine how frequently we need to perform a refresh. So let's demonstrate a refresh. I kind of showed one before. I've now activated the memory cell. I've set the memory cell high, and over time it dims, and as I showed before, if I push the row select one more time while it's dimming, it will light up again. And what I'll show next is, this is going to be a bit quicker because it doesn't last as long when the column amplifier is low. But what I'm going to show next is sending the column amplifier low, and then as the LED dims, performing a refresh again. And what will happen when I do that is the column amplifier will go back into the high state because it will be copying the fact that the memory cell is in the high state. So the column amplifier will go off when I push the off button here, but then when I push the row refresh button, both LEDs will come on fully. So here we go. I'm going to put the column amplifier into the low state and strobe the row select. I did that within like a second there when it came back on. Let's do it a few more times to demonstrate that better. So each time I turn off the column amplifier, the memory cell starts losing its charge much more quickly, but when I push the refresh button, it copies its on state back into the column amplifier. And if I leave it off for a few if I leave the column amplifier off for a few seconds and I don't refresh the memory cell quickly enough in that state, then eventually it will forget its contents. So let's try some longer periods, and you should be able to see that. So that wasn't long enough. That was like 1 second. Let's try about 2 seconds. That's about 1.5 seconds. That was 2 seconds and that stayed off. So let's turn it back on again. Do that one more time. 1, 2, pulse, and it didn't come back on. But if I do it more like 1 second, it comes on much more quickly. So that's all as expected. That's how dynamic memory is meant to work. You need to refresh it on a regular basis, otherwise it loses its contents. I'd like to show you a different angle on this though, which is the case where the dynamic memory is storing the off state, but the column amplifier is in the on state. Because, well, when the column amplifier and memory are both in the off state, it's very stable in that condition, and it will actually remember that forever. This is sort of the state it gravitates towards. If I activate the column amplifier again, then strobe the row select, because that's been on for a few seconds, you can actually see that when I strobed the row select, the memory cell actually turned on then, and that's not what it should do. It's forgotten that it was meant to be off. And once again, that's because we're not strobing it frequently enough. If I put everything into the off state, if I activate the column amplifier and then rather quickly strobe the memory cell, it will just turn off the column amplifier again. So let's try that. Column amplifier on, strobe, and everything's off. And it takes a few more seconds this way round before it actually gets into the broken state. That was about 3 seconds there, I think. Try 2 seconds. 1, 2, 3. So it's a little bit more stable in this state than it was in the on state, but again, we need to strobe it at least once every second or so, otherwise it will forget its state and turn on when it shouldn't, like that. But overall, this is working pretty well. I'm pretty pleased with that. I chose the component values to achieve this kind of decay time because it's very visible. Moving forwards, I'll stick with this for now, but I'll probably be looking to speed things up a bit and reduce some of the resistor values and probably reduce the capacitor value over time if I want to be connecting this to a proper computer, because I think it's probably a bit slow at the moment. But before that, what I'm going to do is build a few more copies of this, because it's quite a nice compact little circuit here. The way this is going to scale up, the memory bit is going to be replicated horizontally along the row, and the green row select line will be common to all of the memory cells along that row, and that little yellow wire in there is the bit line, and that will be shared between all of the columns. So here we are with more rows and columns in the grid. I've expanded the circuit to have 3 rows here, and these are the row select buttons, which will strobe the rows. And there are also 4 columns here, and there are 4 pairs of on and off buttons to turn on and off the data lines going to the columns. So this is now forming an array of 3 words of 4 bits each. Just to remind you, the bottom LEDs are not part of the memory. Those are showing the current states of the data lines, which are the inputs and outputs of the memory block. The remaining rows of LEDs are the 3 words of 4 bits that are being stored. And the top row I ran out of yellow, I'm afraid, so I had to use some reds and some greens. I don't seem to have a very good selection of LEDs here. So let's have a look at how that works. There is some slightly weird behavior going on with it, but it does function. So let's turn it on. They all tend to come on at the start. You can see some of them have dimmed off already because they weren't being refreshed. The rest haven't, and for some reason that right hand row seems to always go off before the others do, and then the others sort of go off a little bit randomly afterwards. I'm not totally sure why that is. Anyway, what we can do is, if I just refresh all of the rows there, we seem to have some numbers in them already. And what I'm going to do is I'm going to keep refreshing them one at a time at this sort of rate. And then I'm going to try and program some numbers into them. So to begin with, let's set the top row all on. And you can see that that's being maintained. It does dim away, but it comes back again. And you can see when I press the row strobe for the top row, the data lines all come on, mirroring the top row. And when I push the row strobes for the other rows, that right hand one is going off, because in the other rows that right hand one is not set. Let me turn this one off now. And now you can see all 3 of the numbers showing up on the bottom row here. Let's do something a little bit more interesting now. We can just turn quite a lot of them off maybe. So now there's just those 3 LEDs are set. So the top word has the right hand LED set, the middle one has the second from the right, and the bottom one has the second from the left. And as I press them, it's copying them down to the bottom. So this seems to work pretty well. As long as I keep pushing it. If I stop pushing these buttons, it will drift into random states, but as long as I give each one a refresh about once every second or once every 2 seconds, it seems pretty stable. So that's that. So in terms of complexity, there are more components here than are needed. About half of the components in the main grid are there to service the LEDs. And again, down in this bottom row here, about half of them are also there just to light the LEDs up and give them some amplified power without drawing too much current from the storage array. So it would be possible to make a more dense array of memory here if I removed all the LEDs, but I quite like having the LEDs there. It's quite nice being able to see the states of the individual bits. I'd hope that the LEDs would dim at the same rate as each other, which would sort of give a bit of a clearer representation of the refresh and of the sort of fading and refresh. It'd be nice if the whole row dimmed at the same time. I'm not totally sure why it doesn't. Anyway, it seems to work pretty well. I'm pretty pleased with that for now. So I'll call that a proof of concept. As for next steps, as I've said before, one of my goals here, I think, should be to hook this up to the 6502 computer. I'll probably do that next. I might hook it up to an Arduino or something, just to have an easier environment to test how quickly I can make it run. It also strikes me that this would be a interesting addition to the 8-bit computer build. I haven't built the 8-bit computer myself. I don't think I have the patience to build something quite that large, but if anyone who has built it is interested in hooking it up to a hand-built memory array like this, I think that could be a really interesting project, and I think it probably isn't very hard to do. Anyway, I hope you liked hearing about that and seeing it built and working. Do let me know, as usual, if you have any questions, and as always, I'd love to hear if you're having a go at building something like this yourself, and any differences that you're making in your own design would be very interesting to hear about. So I hope you enjoyed that. Like, subscribe, notifications, etc. if you want to see future videos in this series or any videos I make on other topics. And see you next time.